When we're looking at skewness, this is going to look at the symmetry of the distribution. So in a normal distribution, such as this red curve in the center, this is symmetrical, right? If we split it down the middle, the right half looks like the left half and vice versa. Okay. When we have positive skewness, represented by this blue shaded region, or this left curve over here, you can see that we have a tail that extends to the right of the mean, or the right of the center of the distribution. The best way that you guys can remember positive versus negative skewness is where the tail is. Okay, so the tail is just the extended version that's kind of far away from the peak. Positive skewness is going to be where the tail is towards the positive standard deviations. Negative skewness will be where the tail is towards the negative standard deviations. So what these indicate is that positive skewness, you would have an outlier above the mean. Negative skewness, you'd have an outlier below the mean. Okay. So positive skewness, tail extends to values that are greater than the mean, which means that our calculations of central tendency are no longer going to be equal to each other. The mean and the mode might still be relatively similar because they're not really affected by extreme scores, but the mean is going to change. So you can see positive skewness if our central tendency should relatively be centered around this peak, right? When we have an extreme score that exists out here, the mean is going to shift towards that tail. In other words, the mean should be greater than the median and the mode, or vice versa, the median and the mode are less than the mean. In negative skewness, it's just the reverse. So now we have a tail on the left that is below the mean, okay, or extends to values that are lower than the mean, which is going to drag our mean towards the tail. So now our median and mode should still be kind of close to the peak, and our mean will get dragged this direction. So it would be less than the median and the mode. So this skewness is particularly looking at when you have an extreme score to one side of the distribution. Kurtosis is another way that we can describe curve shape, and this is looking at the number of extreme scores. So do you have a lot of them? It could be on one side, it could be on both sides, or do you have very, very few? Positive skewness, so let's orient ourselves. Our normal distribution is the one in the center, this one here. Positive skewness is going to be when you have a really tall peak and elongated tails out here. It doesn't look like it in this picture, but just imagine that this line extends very, 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 very close to the x-axis. Okay. So positive kurtosis is characterized by a tall peak, long, and what we call heavy tails, so they sink towards the x-axis, if you will. And those long, heavy tails are going to be indicative of a lot of outliers, right? So when we create our normal distribution, we have a frequency distribution. That frequency distribution is like, think of a bunch of bars. We overlay the curve on top of that. In a positive kurtosis, you might have one occurrence of a lot of different values, and then a really large jump in frequency value. And then that's followed by a lot of small occurrences, or very few occurrences of values above the mean. So we end up getting these heavy tails. So positive kurtosis, tall peak, heavy tails, indicative of a lot of outliers, or many outliers. Negative kurtosis is the opposite of that, where the peak is more flattened, okay? And in this instance, the curve in general is just more of a flat shape in general. So flat peak, light tails, meaning that they float off of the x-axis, right? And we don't really get that dip back down on either side. It's just kind of like flat. And this is indicative that you have few to no outliers, right? So if every value is occurring relatively at the same frequency, none of those values are really extreme anymore within the range of data that you have. So again, kurtosis looks at the number of extreme scores. Positive kurtosis, you have a lot of extreme scores. Negative kurtosis, you have very few extreme scores. Okay. When we calculate skewness and kurtosis, we have a series of calculations that we go through. I give you guys some examples in the activity this week, so they should help to make sense there. But in terms of the formulas, we use z-scores of skewness and kurtosis to help us understand how a sample distribution would look compared to a population distribution. So when we run calculations in SPSS, it'll give us a sample skewness and a standard error of skewness. It's important to remember that sample skewness is not the same thing as our z-score of skewness. The same could be said for kurtosis. Okay? The z-score of skewness and kurtosis are what we are using to assess normality in this class. So if we're using this method at least. Okay, so remember you're taking sample skewness divided by the standard error. The standard error is 6 divided by the sample size, or square root of 6 divided by the sample size for skewness. It's 24 divided by the sample size. Take the square root of that for kurtosis. These are standard scores for skewness and kurtosis. Okay, so again, doesn't matter what the units are that you've collected when you create some type of z-score, everybody's in the same unit now. The way that we evaluate if we have an outlier or if we have positive or negative kurtosis is based on the value that you end up with when you calculate your z-score. So if you have minus 1.96 or less than minus 1.96 for skewness, that's going to reflect negative skewness or negative kurtosis. Okay, so if z-skew or z-kurt is less than negative 1.96, you have negative skewness or kurtosis. If your z-skew or your z-kurt is greater than positive 1.96, we say that you have positive skewness or positive kurtosis. The reasons we've chose 1.96 is that is identified with the 95th and the 5th percentile. In other words, it is the middle, remember the empirical rule, the middle 95% of the data exists relatively between plus and minus 2 standard deviations. So if your sample skewness or your sample kurtosis lie with outside of those regions, that indicates that your sample distribution is relatively not the same as your sampling distribution of your population, which should be normal. Okay. So that is one way to assess normality, using skewness and kurtosis values. Another way to assess normality is using tests in SPSS. So we have the Kolmogorov-Smirnov test. We're not going to use that one in this class. The one we're going to use is the Shapiro-Wilk test. Both of them have a null hypothesis. So I try to explain this a little bit more when we go into our videos. But remember, null hypothesis is true until it is proven wrong. So in this case, the null hypothesis is that we are assuming the distribution of our sample is not significantly different from a normal distribution, which we would say our population should have a normal shape, right? Or the sampling distribution of our population should have a normal shape. So we would expect that our sample also has a normal shape. Okay. If you end up getting a p-value greater than 0.05 in the Shapiro-Wilk test, that is indicative that you would accept the null and accept that this statement is true. In other words, your sample distribution is not significantly different from your population distribution. If you get p is less than 0.05 for the Shapiro-Wilk test, then you would reject the null and you say your sample is not normally distributed. In which case, sometimes you would have to go to your z-skew and your z-kurtosis values and see which one is affecting the distribution shape. Note that it's not always that you're going to have just skewness or just kurtosis. You could have a combination of both. Okay. So that's one way we could check to see why we don't have a normal distribution. The other way we can kind of further look into this is by doing an outlier analysis, which is kind of the topic of our next slide. Outliers we can test in several different ways. One way is using the IQR method. Remember, IQR stands for interquartile range. So we can identify outliers below a lower bound or below the mean by looking at Q1 minus 1.5 times the interquartile range. And then outliers above an upper bound by looking at Q3 plus 1.5 times the interquartile range. Note that this doesn't work on all outliers. It's a certain type of method that we can use. There are other methods out there, so it's not by any means like the only way. We can also use plots in Excel and SPSS, so we can look at box and whisker plots, which will give you your Q1, Q2, and Q3. Usually will show you where your mean lies in that box, and then you have whiskers that extend to 1.5 times the interquartile range. Any values that are located outside of that kind of extending whisker are going to be considered outliers. We can also use histograms, right? If your histogram or bar graph ends up coming out in like a skewed looking way, or it's flat, or it has a really tall peak and a lot of small frequencies on the outside, visually you can kind of assess if you possibly have outliers in your distribution. We can also look at the percentage of z-scores. So this looks at frequencies of values in various ranges of the distribution to assess the probability of outliers. I don't think we really need to touch on this one in this class, but I just wanted to present it because it is another way you can assess if you have outliers or not. As a final note, normality does not need to be investigated for every parametric data set if the sample is large enough. So remember that we said, based on the central limit theorem, that if you have about 30 to 40 subjects, usually in a normal population, you would automatically start seeing that you get a normal distribution shape if you are a sample size of 30 or larger. Okay, so if your sample is large enough, based on the central limit theorem, you usually can assume that your data will be normally distributed. If you have a smaller sample size or a sample less than 30, you usually would want to run normality tests just to make sure that your sample is normally distributed. Okay. Ways to check normality on samples, particularly small ones. We can do significance testing. For us, we're going to use the Shapiro-Wilk test for normality. You can use plots, right? So histograms, we can use density plots, which I'll show you guys in SPSS in your activity, box and whisker plots, etc. And then we can calculate z-scores for skewness and kurtosis. So in exams or in quizzes, sometimes I'll ask you, like, what is the, assess the distribution shape. How would you describe the shape of the distribution, right? And you can use any one of these methods to justify your answer for how you would describe the shape of the distribution.